Hello and welcome back. Today we are going to tackle 8.5, logarithmic regressions. So logarithmic regressions are again performed very similarly to other regressions we've done so far. We have our base equation that we're always going to be using, but when we do the regressions, we're going to do a couple things. We're going to enter our data into a table on Desmos. We are going to use x1, y1, and a squiggle rather than x, y, and an equal sign. Desmos is going to spit out a values and b values for us that we're going to insert back into the original equation, and that's it. Nice. So we're actually going to jump right into some regression examples, and here we have Rosalind. Rosalind is researching the rise in the tuition fees for post-secondary education in Manitoba for a project on inflation. She found some data that uses the tuition fees in 1992 as a benchmark, assigning them a value of 100%. The tuition fees in all the other years are then compared with the tuition fees in 1992. So, here we have our table of values here. Something to keep in mind that you always want to look at what your table of values is talking about. So we have the year, and we have tuition fees as a percent of the cost in 1992. Before we just go ahead and plug this straight into Desmos, we need to make sure we understand which variable represents our x and which variable represents our y, okay? When we're talking about what goes on our x-axis, that is always our independent variable. And time always acts as our independent because that is going to continue going on regardless. Our tuition fees, well, that's based on the year it is. Right? So it becomes our dependent variable, which is our y variable. Okay? So I took the liberty of plugging this into Desmos already, but notice that under my x column, I put all of the years, 1979, 1982, 1984, and so on. In the y, I put all of my percent values, so 37.8, 43.8, 54.0, and so on and so forth. Okay? If you swap them around, you will get a different and incorrect equation. So you need to make sure you ask yourself, is this x or is this x? Right? Which one is the independent variable and which one's the dependent variable? Because it won't always be given to you in order. All right, that's my spiel. Once we're in Desmos here, we might want to change our scale so that we can see our data points. So our x values go from 1979 to 2006. I might want to extend that a little bit further, so I might go 1975 to, 2010 maybe. And for my y value, it's anywhere between, it looks like the lowest one is 37.8 all the way to up to 305. Maybe I'll go a little bit negative. I'll go -5 all the way to 350, just to give me a little bit of a range here. Okay. It asks us to a logarithmic equation, so we are going to be using our logarithmic regression. So we have y1, we have our squiggle, a plus b ln x1. And we should get something that looks like this. Right? And if we zoom out, it looks quite logarithmic. When we zoom in, you might be thinking, well, that kind of looks like a straight line. Right? So don't let that affect you. Don't let that freak you out a little bit, because realistically, when you're zoomed into a little part of the graph, you don't see the big picture. So if you just want to double check that that is in fact logarithmic, you could zoom out and then you could see what it'll actually look like. All right, we want to determine the equation here. Well, we've done our regression, and we get an a value of -164,440 and a b value of 21,664.1. So when we plug that into our equation, we get y is equal to a, which is -164,440, plus b, 21,664.1, ln of x. You'll notice whenever I draw my L for my ln, I always do a cursive L, and that's because sometimes drawing an L and a 1 look crazy similar. especially if I were to do that here, you'll notice that I have a 1 right before that ln. So I always tend to write ln with a cursive L just to help let you know what I'm trying to indicate and myself know what I'm trying to indicate down the road when I look back. Let's get this highlighting away. All right. So the next question, they're just questions based on our graph here. So it says, what year would the tuition fees have doubled since the benchmark in 1992? So if 1992 they were at 100%, we want to know when or what year our percent would have been 200, right? If it doubles, it's 200% if it was 100 to begin with. So we go y is equal to 200, and we get this point here. So, we get an x value of 1997.548, right? So that would have happened. The tuition fees doubled in 1997. Right, I realize it's 1997.548. Usually you'd think, oh, round up, but that happens within the year 1997. Capiche? All right, if this model continues, what do you think the tuition fees would be in 2020? So that's when our x value is 2020. X equals 2020. And our tuition value, so if x is the year 2020, y represents our percentage, which is 442.142. So we would say that our tuition fees in 2020 would be 442.14% of that 1992 tuition. So it would be 442.14% of the 1992 tuition. So essentially, it's 4.42 times as great as that tuition was in the year 1992. Okay. Lastly is our domain and our range, and this could get a little bit tricky here. Because when we're talking about our domain and our range, in word problems, we have restrictions. And these restrictions are much more prominent and much more important when we're talking about logarithmic graphs. So please make sure you're paying attention here. So, when we're talking about restrictions, really what we want to ask ourselves is, what values on the graph do not make sense? Okay, so that's what we're asking ourselves. We'll just put Desmos down a little bit here. So in our two variables, we are talking about years, and we are talking about our percent of tuition. Okay? If we are talking about years, obviously years can't be negative, and years can go on forever. Right? So that's one thing that we might want to notice. So for years, we can't have negative. When we're talking about percent, we can't have negative either, and our percent can continue on. Right? We could have up to 1,000,000% if we want. Right? It just talks about the rate of increase from 1992. But we can't have negative years, and we can't have negative percent. Very often, when we are talking about restrictions, one will affect the other. One will limit what makes sense in our data. And in this case, I'm going to just mute the green here. But in this case, when we're talking about our years, our years talk about the x-coordinate, our percent talks about the y-coordinate. Our y-coordinate hits a value of 0 before our x-coordinate will, right? Because our x-coordinate will never hit 0. So if our y-coordinate hits 0 in the year 1979, that means our percent is 0 in 1979. We can't be talking about data values before 1979 because it gives us a negative percent, right? If we went somewhere here, it gives us a negative percentage, which means even though those years can be graphed with a logarithmic function, those values don't necessarily make sense in the context of our word problem. So the limiting factor here is going to be our percent, because our percent can't be smaller than 0. So we are going to say our graph, because I can't really write on decimals here, starts at that point and then continues on forever. The points below that, this guy here, will not make sense because we cannot have a negative percent value. So when we're talking about our domain and the range, in context to this question, there are restrictions. So how would we indicate that? Well, our domain is everything from that point onward, right? So our domain would include 1979.192 all the way to infinity, and our range would include 0 all the way to infinity. Okay, so our domain and our range are restricted and can only start at that same point. So even though when we were talking about our restrictions originally, we said, well, years can't be negative, so years can start at 0 and go on forever, our years are going to be restricted even further by what our percent is restricted by. They start at the same starting point. We can't have one start at 0 and the other start at 0, because there's going to be a whole section of points, these guys, that won't be able to exist. Okay, and that's, I think, probably the trickiest part. All right. We have one more question here, and we have Bianca, and she enjoys a Starbucks chai tea. It's 180 degrees with no water, no foam. Very specific. Bianca tries to avoid drinking it in the afternoon because it affects her ability to go to sleep at night. After some research, she found a study that looked at how fast a person metabolizes caffeine. Each person started with 200 milligrams of caffeine in her or his bloodstream. The results of the survey can be found below. So we have caffeine levels in milligrams, right, if they start at 200, continuing on, and the time after ingesting, so the hours in which that continues on. First thing that it asks us to do is to sketch a scatter plot. So, when we are sketching a scatter plot, remember that is just drawing those points that we have, but notice it doesn't ask us to draw in a curve of best fit. If it wanted us to draw a curve of best fit, it would go ahead and ask us to, but because it just says scatter plot, scatter plot, we are just plotting the points. We are not drawing in a curve of best fit. But we are going to continue on with all of the other things that are important in a graph, like a title, and labeling our axes, and indicating a scale, and all of that fun stuff. So, first of all, let's figure out what represents our dependent variable and what represents our independent variable. Okay? Our time after ingesting, we have time and we have caffeine level. Okay? How much caffeine we have in our bloodstream will be affected by how long since we've had that caffeine product. So time is going to be our independent, which means time goes on our x-axis, and the amount of caffeine depends on that, so is our y, goes on our y-axis. So we're going to go ahead and write those variables on our axes. So time after ingesting and our time is given to us in hours. And our caffeine level. And that's in milligrams. Okay. So we've labeled our axes. We have units, which is awesome. And then we also want to indicate a title here. So a good title should tell us a little bit about what's going on here. So we might just say caffeine level over time, or versus time. Okay. At this point, we also need to indicate a scale. Okay, so we have our X and our Y axes labeled. Life is good. So when we're looking at our X-axis, we're looking at these values here. They go from 0, essentially, or 1 to 14. So if you look, we should be able to go up maybe by 2s. Let's try it out. 0, 2, 4, 6, 8, 10, 12, 14. Right? If we go up by 1s, there's not going to be 14 there. And we want to try and spread out our graph as much as possible. So we can't go up by 1s. We'll try going up by 2s, and it worked out for us. In terms of our Y, we need to figure out a scale for that. Obviously, we can't go up by 1s. We're going up from 0, essentially, to, like, I don't know, 168. Okay. We won't be able to go up by 10s either. There won't be enough lines. But what if we try going up by 20s? So 0, 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. It looks like we just made it. So that's awesome. Remember that we always want to make sure our scale is spread out as much as possible when the space provided, because otherwise that could result in lost half marks or communication errors. At this point, we are just going to plot our values. So at 1, we have 168. So X is 1, Y is 168. When X is 3, we have 145. When X is 5, we have 112. When we have X is 6, we have 100. X is 6.5, we have 90. 7.5, we have 80. 9, we have 75. At 12, we have 55. 13, we have 45. And at 14, we have 33. Okay. Again, your points don't have to be perfect. No one's going to be using a ruler to figure out if it's exactly on the nose, but you want to try your best you can to see if you could plot those points in a reasonable spot there. Okay. We are then asked to determine the equation of the logarithmic regression. So I'm going to open Desmos back up here. I'm going to get rid of all the things that we had before. And I'm going to plug in my values. So my X, remember, is my time. So I'm going to plug in 1, 3, 5, 6, 6.5, 7.5, 9, 12, 13, and 14. Just double checking that I plugged in all of my values properly because I don't want to lose any silly marks. Then I have 168, 145, 112, 100, 90, 80, 75, 55, 45, and 33. And again, just double checking over these values to make sure we are on board. It's always important to take the time to make sure that you've plugged in these values correctly because just having a simple mistake could change the equation drastically. So it's always better to take your time and double check them as you're going, instead of going back and plugging in all the values again. Okay. We also might want to change our scale, because right now our decimals just looks like a small little dot. So to do that, I'm going to do the same thing. Maybe I'll make it match our graph. So I'll go from, our x can go from -2 all the way up to 18. And our y can go up from -20 all the way to 200. And our graph looks pretty similar, so that's a good sign. It means that we've done a pretty dang good job, so yay us, cell 5. And we're going to plug in that regression equation. So y1 squiggle a, y1 squiggle a plus b ln x1. Alrighty, so here we get an a value of 185.251 and a b value of -51.9634. And we are going to plug that in to get our regression equation. So y is equal to 185.25, we're going to keep it to 2 decimal places here, minus 51.96 ln of x. And that is our equation. Oops. Beauty. All right, determine the time it takes for an average person to metabolize 75% of the caffeine in their bloodstream, round to the nearest tenth of an hour. Okay, couple of things to keep in mind here. We are asked when the person has metabolized or processed 75% of the caffeine in their bloodstream. In this study, each person started off with 200 milligrams. Okay, so if they've metabolized 75%, that means there is 25% left in their system. Okay, maybe I'll write that down. So if you start with 200 milligrams and metabolize 75%, you have 25% left in your system. Okay, so 200 times 0.25, what you have left in your system is going to be 50 milligrams. Okay, so we can't plug in y is equal to 75 because our y doesn't give us our caffeine level in percentage. Y gives us our caffeine level in milligram. And we're not multiplying 200 by 0.75 because that would tell us how much we've already processed. It would give us 150, so we'd have to subtract that 150 from the 200 if we wanted to multiply it by the 0.75. Okay. So we want to know how many hours later after ingesting they would have 50 milligrams in their bloodstream. So we could plug in y is equal to 50 and get that intersection. So at 13.502 hours later, so 13.50 hours after ingesting. Alrighty. The next one, if Bianca had her chai tea that contained 200 milligrams of caffeine at 10 a.m., how much caffeine would be in her bloodstream at 9 p.m. that evening? Round your answer to the nearest milligram. Okay, so again, our time is not 10 a.m., our time is not 9 p.m. Our time represents hours after ingesting. So from 10 a.m. when she's ingested all the way to 9 p.m., that is a total of 11 hours after. So that's 11 hours after ingesting, which means our x is 11, and we want to figure out our y. So we go x is equal to 11. and we get 60.648 milligrams. But the question asks us to round to the nearest milligrams, so that would be 61 milligrams in her bloodstream. Last question. If her caffeine levels must be below 41.2 to fall asleep, and Bianca usually goes to bed at 11 p.m., what is the latest time that Bianca can enjoy her chai tea latte round to the nearest hour? Okay, so for starters, we want to know how long it will take for her to only have 41.2 milligrams of caffeine left in her bloodstream. So we want to know when Y is 41.2 milligrams. Okay. So Y is equal to 41.2. And we get that as 15.993 hours after ingesting. And since we're rounding to the nearest hour, that's 16 hours after ingesting. Okay. If she goes to bed at 11 p.m., that means she had to consume that chai tea latte 16 hours prior to, right? Because it takes 16 hours for her body to process that and get to a level of 41.2 milligrams, which means if she goes to bed at 11 p.m., she needs to have had that chai tea latte 16 hours before. So if you count backwards, 16 hours before 11 p.m. is actually going to be 7 a.m. So Bianca must have her chai tea latte at 7 a.m. in order for her body to process enough of that caffeine so that she can fall asleep at 11 p.m., which is just straight up crazy. Alrighty, that's it. That's all for 8.5. So that's what our logarithmic regressions look like. Because we have done regressions now with all these different polynomials, we've done this with exponential. You'll notice that some of the questions that we did today got you thinking a little bit more. They didn't give you information in the most obvious way. Sometimes you had to go and calculate it yourself, or think about it, or process that information a little bit more prior to going ahead and plugging in values into Desmos. That is something that you can expect to occur essentially from now on. You want to make sure that you understand what the question's asking of us and making sure that you're doing all this work properly. So we had some questions that involved some deeper level thinking today, and hopefully you could continue that deeper level thinking in today's homework. All right, that is it for me. Take care. Peace out. See you soon.